Hello there, BC Calc, section 3.4, the chain rule, with some extra fun stuff on parametric curves. This is what I would like to emphasize today. Class opener for today is if big F of x is equal to f of g of x, then what is big F prime? Well, we know the chain rule prior to that big F prime would equal the derivative of the outer, leave the inner alone, times the derivative of the inner. Now, this little box here, this little setup, I actually wanted to talk about that we can, if we have, let's say, x of t and y of t, that we can find dy dx. dy dx will be dy dt, which is the change in y with respect to time, over dx dt, which is the change in x with respect to time. So dy dt over dx dt, dy dt over dx dt is the same as dy dt times dt over dx, which, look at that, gives us dy dx. The dt's cancel, and I get dy dx. So just for future reference with regards to parametrics, dy dx can be found by taking dy dt times dt dx. Okay, so let's look at some chain rule derivatives just to get a little refresher. Sine of f of x, well, if I use the chain rule, I'd take the derivative of sine, which is cosine, leave f of x alone, and then multiply by the derivative of the inner function. Okay, very similarly, derivative of cosine is negative sine. Leave the inner alone, multiply by the derivative of the inner. Tangent, derivative of tangent is secant squared. Leave the inner function alone. You get the picture here. Multiply by the derivative of the inner. E to the f of x, well, that'll stay the same. And then we'll multiply by the derivative of the inner function. A to the f of x, well, the derivative of a to the x is ln of a times a to the x. In this case, that'll be f of x times the derivative of the inner function. Little product, or excuse me, chain rule work there. Let's look at a couple more examples. Derivative of e to the square root of x. Well, e to the anything will stay the same times the derivative of the square root of x, which ends up being 1 over 2 root x. So we could rewrite that, keeping it clean here. Derivative of e to the square root of x. Having some proper notation, I'd have e to the square root of x over 2 root x. Okay, how about the derivative of 5 to the negative 1 over x? Well, that will be the natural log of 5 times 5 to the negative 1 over x times the derivative of negative 1 over x. So let's work that over here. I'm going to write that as negative x to the negative first. All right, that's equivalent to negative 1 over x. Therefore, that would be, I'd bring down the negative 1. Negative 1 times negative 1 would be positive 1, x to the negative 2. So the derivative of negative 1 over x is 1 over x squared. So I would write this over x squared. There you have it. There's some chain rule. All right, love it. Let's move on and talk a little bit about a couple of AP problems, and then we'll get into some parametrics as well. Example 3 here gives us that f of x equals x squared minus 4, and g is a differentiable function. What is the derivative of f of g of x? Okay, so I would first write this in general form. So the derivative of f of g of x would equal f prime of g of x, as we know from above, times g prime of x. Okay, so let's look at the derivative of f. So f of x was x squared minus 4. So f prime of x would equal 2x. So f prime of g of x would equal 2 times g of x. So I'm going to replace f prime of g of x over here. Let's highlight this in a separate color with 2 times g of x, and then times g prime of x. I think that should be enough, and it is. It looks like our answer for this particular question is D. All right, let's continue. All right, example 4 looks like a little bit more work with the chain rule. Let's do it. F of x is a e to the negative ax for a greater than 0. Find f prime. Okay, so I'm going to keep the a e to the negative ax, and I'm going to multiply by the derivative with respect to x of negative ax. Well, that'll be negative a. So I'm going to multiply this by negative a. So our derivative would be negative a squared e to the negative ax. Let's see if we've got ourselves an answer here. And we do. That is E. Okay, chain rule is starting to become second nature. Okay, example 5, non-calculator example. If y equals x squared minus 2x and u equals 2x plus 1, then what would dy du equal? Okay, so now think of this very similar to how I define this with dy and dt, right? So dy du will be equal to dy dx over du dx. Okay, so let's find dy dx, or y prime. Dy dx will equal, based on the function given above, that'll be 2x minus 2. Du dx will be 2. So dy du will equal dy dx, which is 2x minus 2, over du dx, which is 2. So dy du, if I factor out a 2, looks like it will be x minus 1. All right, looks like our answer here is D. So that's a chain rule component that we're going to see show up here in a little bit with parametrics. Okay, so let's talk some syntax here in example number 6. All right, when it says it has this little bubble looking thing right here, that means that W is equal to U of V. Okay, so the function V, okay, so let's say h of x equals f of g of x. G of x is like V in this case, and f is like U, and h is like W. We just don't have an independent variable defined here. This could be, W of t is U of V of t, whatever it might be. I don't know, and honestly, I don't care. But all of this garbage that's given to me, what I want to do is find W prime is 0. So I'm going to write W prime, and now I'm going to use the chain rule. This will be U prime of V times the derivative of the inner, which is V prime. So W prime is 0. It's going to be U prime of V of 0 times V prime of 0. Okay, so V of 0, let me do that in a different color just for a moment. V of 0, I think we're given up here, yeah, we're given 2. Okay, and V prime of 0, we're also given, and it's 5. Okay, so W prime of 0 will equal U prime of 2 times V prime of 0, which is 5. All right, so what is U prime at 2? U prime at 2 apparently was important enough to put up here twice. That's maybe an indicator. Hopefully AP didn't do that. But that would be 4. And of course, V prime at 0 is 5. So W prime at 0 is 20. I think the biggest hang up on this problem would be students deciding, is that multiplication or is that some kind of composition? And anytime you see that bubble looking thing, that's a composition. The second function will be the inner of the two functions. All right, let's continue with some information on parametrics, and then we'll get into some applications of those. Okay, for the sake of time, I'm not going to be proving the total distance, nor the speed, or the total displacement, but I do want to talk through each of the following bullet points here. So when we talk about parametric equations and tangents to parametric curves, we need to talk specifically about x of t and y of t. So x of t is an independent function that tells you what the horizontal movement of the particle will be based on time. And y of t is the vertical movement of the particle or the object with respect to time. So we can define those independently, but still be able to work with our traditional methods of finding tangents to these curves. The velocity vector, v of x and v of y, is just another way to kind of organize this method of looking at the change in position, right? You could refer to this as x prime of t, y prime of t. Gives you functions for the velocity. And then the acceleration vector in a very similar way would be x double prime of t and y double prime of t. So if I wanted to know, the acceleration of the particle at a certain time with respect to its y value, or its acceleration in the direction of y, I could just plug it into the the acceleration vector just into that function. So these will be functions, right? They will be position, velocity, and acceleration functions for the particle with respect to x or with respect to y. Okay, now the slope of the tangent line we've talked about a little bit, right? dy dx, or the slope on the curve. Say the curve looks like this. That's not a function, but I can, using dx dt and dy dt, find dy dx. Okay, I can find dy dx. All right, speed is given by using the distance formula. So speed, simply put, is the change in direction of the x squared plus the change in direction of the y with respect to t squared, which is the same form as you'll see here. dx dt squared, dy dt squared, add them together, take the square root. That comes directly from the distance formula. Okay, and then the total distance traveled. Now the total distance traveled, let's say at time t equals 0, the particle is here, and at time t equals 8, the particle is here. The total distance traveled would be calculating the length of that curve, right? And that can be done by using the following. I am not sure why there's two sets of absolute values here. There should only be one on both total distance and total displacement. But that's how you would find the total distance, total displacement, taking the integral from time t equals 1 to t equals 2, so in our case from 0 to 8, of the absolute value of the square root of the change in x squared plus the change in y squared with respect to t. Okay, now with respect to that, a curve has a horizontal tangent when dy dt is equal to 0. So the particle is not changing its position vertically, right? Its velocity in the y direction is 0. And it would have a vertical tangent when dx dt is 0. So there's no horizontal movement when dx dt is 0. In both cases, we cannot have 0 over 0, right? So if dy dt and dx dt are both 0, what we have is actually that the particle is at rest and it's changing its direction. So the particle is at rest because there's no movement. It's at rest when both dx dt and dy dt are equal to 0, which makes sense, right? If it's not changing direction in the x or in the y direction, then we know that the particle is at rest. Now it could come to rest and then again begin movement in the same direction that it was. It could come to rest and come back toward the origin. We don't know. That would be based on the specifics of the parametric equation. All right, let's apply this information to an example. Let's find an equation of the line tangent to the parametric curve x of t equals 2 sine of 2t and y of t equals 2 sine t at the point square root of 3, 1. Okay, so the first thing I need to know is I need to know the time at which the parametric equation is located at the point square root of 3, 1. I can do that in two ways. I'm under the assumption that both the x at that time and the y at that time should be at that point. So at the same time, they're at that point. So I'm going to set x of t equal to square root of 3, right? My x at a certain time will be at square root of 3. My x at that same, or excuse me, my y at that same time. Of course, these times, based on the fact that the problem gave me that point is on the curve, I can assume that those times are the same. So I'm going to do, actually I might do the easier, the two calculations. I'm going to work with y of t. So y of t equals 1 at a certain time. So I'm going to solve for t to find that time. Divide by 2, I get 1/2. And then it looks like, I goofed that up. How about 1/2 is equal to sine of t? And the sine of t is equal to 1/2 when t equals pi over 6. Okay. So this would be the first time, right? The first time that the function would be at that point. Now it could potentially be there again, depending on, because the sine of t is 1/2 also at 5 pi over 6. So this would be the first time that this would happen. Okay, so now, if I want to find the equation of a tangent line, I need two things. I need a point, which I have, which is the square root of 3, 1, and I need a slope. I need to know dy dx at the time pi over 6. Okay, so dy dx, of course, is dy dt over dx dt. So I want to know dy dt at the time t equals pi over 6. And I'm going to divide it by dx dt at the same time. All right, so I got a little bit of work to do. Let's find dx dt. That will equal 2 cosine of 2t times 2. So let's make that first 2 a 4. Okay, so dx dt at t equals pi over 6 would equal 4 times the cosine. 2 times pi over 6 is pi over 3, I believe. Yeah, pi over 3. Cosine of pi over 3 is 1/2. Therefore, dx dt at t equals pi over 6 would be 4 times 1/2, which would be 2. All right, dy dt would equal, well, that would be an easy one, 2 cosine t. So dy dt at pi over 6 would equal 2 times the cosine of pi over 6, which comes out to be 2 times the square root of 3 over 2, which would be the square root of 3. Okay, now to find the slope of the point, at that point, we would take dy dt over dx dt, which would equal the square root of 3 over 2. Thus, our tangent line equation, I'm going to actually put it up here, our tangent line, because I ran out of space, what the heck, would be y minus y. Well, we know our y value is 1. Our slope is the square root of 3 over 2. And x minus x, we know our x value was root 3. And there is your tangent to the parametric curve at the point square root of 3, comma 1. Okay, let's look at one more example here. The position of a particle in the xy plane is given by this parametric x of t and y of t. At which of the following points is the particle at rest? Okay, we said that the particle is at rest when both dx dt and dy dt are 0. So I'm going to look at dx dt and dy dt, set them equal to 0. So x prime of t is the same as dx dt. And that's going to equal 3t squared minus 6t. Okay, 3t squared minus 6t. Let's set it equal to 0. Factor the greatest common factor out of it. That would be a 3t. That would leave us with t minus 2. So dx dt, or x prime at 0 equals 0, right? Because t would equal 0. And x prime at 2 is equal to 0. Okay, let's look at y prime. Y prime at t, or the change in y with respect to time, would be based on the following function, 12 minus 6t. So if I set that equal to 0 and factor out a greatest common factor, I'm going to take a 6. That would be 2 minus t. So it looks like y prime at 2 should equal 0. Thus, okay, we know that the particle is at rest at t equals 2. All right, that doesn't answer our question though. It wants to know at which of the following points. So if I know at t equals 2 that the particle is at rest, I'm going to find the position at time 2. So that would be x of 2 would be 2 cubed minus 3 times 2 squared. So our x position, we'll see if we can eliminate some answers, would be 8 minus, would that be 12? So our x value would be negative 4. It looks like we've got our answer right here. Let's just confirm with our y value, just in case we goofed something up. Y of 2, we'll plug a 2 into y of t. That'll be 12 times 2 minus 3 times 2 squared. So that looks to be 24 minus 12, which would be 12. So it looks like at the point negative 4, 12, the particle is at rest. All right, I'm going to pause on these notes and call this part 1. We'll see you in part 2 for some FRQs.